Thank you very much for the introduction. So yeah, we'll be talking about a proof system for unsolvable planning tasks, and this is joint work with Gabriele Röger and Malte Helmert. So in general, it is desirable that we can verify if the output that the planner gives us is actually correct, because it might be incorrect for several reasons. One of the reasons I'm sure you're all familiar is that software bugs always happens, but it can also happen that we have hardware faults, or maybe even malicious reasons might be behind it. So how can we validate this? If the planner gives us a plan, then we can just see if the plan is applicable and leads into a goal state, and we have tools for that like val and inval. Now, if the planner claims unsolvability, then for this, last year we introduced also here at ICAPS the notion of inductive certificates. And this is basically inductive certificates in a nutshell. So the idea is that we try to find a set of states with three properties. The first property is that there are no successors of the states, and with this I mean if you take any state in the set, you apply an action, you will still land in the same set, so there is no way out. It's basically like an invariant, you could also say. And now if such a set contains the initial state, but does not contain the goal state, then this is a sufficient argument for unsolvability, because there is no way that you can get from the initial state to the goal. Now, the weakness that we have with this approach is that it is not compositional, so we need to find like this one big set, and we have also seen last year that we can, for example, we could cover heuristic search with merge and shrink, say, or heuristic search with the H2 heuristic, but we could not create a certificate for heuristic search with the maximum of these two heuristics, because they require different representations, and we could just not put it together. So this was the incentive for our new approach now, which is based on a proof system. First of all, what is a proof system? The basic idea of a proof system is that we try to collect knowledge about certain objects in our world. So my example here is from set theory. Let's say we have some sets, concrete sets A, B, C, and we know, for example, the intersection of A and C is a subset of B, or element A is in A, in the set A. And a proof system has two ways of gaining new knowledge. The first one is what we call a basic statement. So here, for example, A is a subset of B. Here we talk about concrete objects. And we just state that this is true. And this means, of course, that the verifier needs to actually verify whether this is true. So a verifier would need to look at those two sets and see if this statement is actually correct. The other way of gaining knowledge is through derivation rules. The example here from set theory is if X is a subset of Y and Y is a subset of Z, then without actually knowing what X, Y and Z is, we know already that X must be a subset of Z. So the idea here is that we take existing knowledge and we derive new knowledge from that, and those rules are actually universally true. So a verifier does not need to take a look at the concrete sets anymore, it just needs to see if the rule was applied correctly. Now, how does our proof system look like? We are talking about state sets in our proof system, and we consider different formalisms that those state sets are given. So in this work we considered BDDs, Horn formulas, 2CNF formula, and explicit set representation, meaning we just list all the states in the set. And we focus on these because they are quite nice in the sense that they can support certain operations in polynomial time. So if you have a general formula, already deciding if a state is in that set can potentially, or okay, that's a bad example, but seeing if the set is empty is already NP hard. But with these formalisms, this is not the case. So the types of statements that we use in our proof system, the most important one is the notion on whether a set is dead. And by that, what we mean there is that there cannot be any plan going through any state of this set. And then we also need a subset or equal relationship, which you see afterwards in the rules why we need that. And we also have the unique statement of the task is unsolvable. Now, here is an overview of the most important rules in our proof system. I will not go through all of these. I will cover the first 5 because they are fairly simple. And rules D6 until D9 are basically the core of our proof system. They are used to show that new sets are dead. And I will just exemplify on D7 how those rules work because they are all quite similar. But first to the first 5 rules. So the first rule is very simple. The empty set is dead because it doesn't contain any states. D2 simply states, well, if we have 2 dead sets, then their union is dead. D3 states, if we have a subset of a dead set, then this set also must be dead, so also fairly obvious. And D4 and D5 are the rules that we need to finish our proof, because if the initial state is dead, or if all goal states are dead, then the task must be unsolvable, because every plan needs to go through the initial state, and every plan needs to go through some goal state. So these are sufficient criteria to show that the task is unsolvable. Now, as I said, for the other rules, I will only take a look at D7. So the general idea is we have a dead set S prime here in this case, and then we have another set, S, and from this set we can only get to S prime. So each successor of S is either in S itself or in S prime. It is of course possible that from S prime we can get somewhere else, but that is not important at the moment. So if we have in this case now that the initial state is in S, then we know that everything that is not in S cannot be part of a plan, because the only way to get outside of S would be over S prime, but S prime is dead, so no plan can go through that. And this is why we can follow from these 3 attributes, so S leads only to S and S prime is dead, and the initial state is in S. From this we can conclude that the negation of S is dead. Now finally, our last part is the basic statements. We are currently restricting only a very small amount of subset relations as basic statements, and these are the statements that we need in order to apply the rules, and also statements that that are verifiable in polynomial time. So this is why we restrict ourselves to this for the moment. So the first one is simply a subset equal relation. The second one we need for rule, which one was it, for as a subset of 2 other sets. We can, for example, use that in rule D3. Then S intersection with the goal is a subset of another set. This we need to show that certain intersections with the goal are dead, which we need in rules D6 and D8, and so on. So these are all just statements that we need for applying the rules. And as I said, we can verify those statements with the formalisms that we consider in polynomial time if all the sets are given in the same formalism. So if, for example, S and S prime are both Horn formulas, but also for B1 we can actually verify this statement also if S and S prime are given with different formalisms, at least in some cases. Okay, this is an overview of the techniques which are used in planning, which we can actually generate proofs from. This is not necessarily an exhaustive list, but this is what we looked at. So we can generate proofs for blind search, both explicit and symbolic, also both in regression and progression. We can generate proofs for heuristic search with 1 heuristics, and there we looked at the delete relaxation heuristics, merge and shrink heuristics with a linear merge strategy, and the HM and HC family. So, and also Trapper, which was introduced by Nir Lipovetsky et al. In 2016. So these 3 things actually our old approach of inductive certificates could already cover, but now the next 2 points is something that we could not do with the old certificates. And that is, as I mentioned before already, heuristic search with multiple heuristics, because we did not have this composability before, and also the H2-based pre-processing, which Alcazar and Torralba introduced in 2015. So I will give 2 examples on how such a proof actually looks like. The first one is how we can translate inductive certificates into our new proof system. As a reminder, inductive certificate is a set with no successor, containing the initial state but no goal state. And now, as you see, the proof now is quite short actually. We first state that the empty set is dead because we need that later. Then this no successor, we just reformulate here a bit more complicated. What this means here, this second point, is the successors of S are a subset of S and union with the empty set. Then the third statement here says basically S intersected with the goal is a subset of the empty set, which is another way of saying S contains no goal. And now we can actually apply the rules from before, because the intersection of S and G is a subset of a dead set. We know intersection of S and G is dead. From this we can then also follow together with the second and the first part of the proof that S is actually dead. And now we just need to show that I is dead, and since we know that I is in S, we can say, okay, I is the set consisting only of I is a subset of a dead set, and thus is dead, and thus the task is unsolvable. For the second example, I wanted to take a look at heuristic search. So how does heuristic search in general a planner show unsolvability? It searches around, it finds some dead ends, doesn't explore those dead ends any further, and at some point it exhausts the search space if you don't consider the dead ends. So basically the heuristic search says, well, all my dead ends are dead, and from my expanded states I only get 2 expanded states or 2 dead ends. So this is also how the proof structure will look like now in our proof system. And an important part here is again that showing that a dead end is dead is actually completely independent of showing that a different dead end is dead. So this allows us to combine different heuristics together, because showing the deadness for the dead ends is done completely independently. So let's see how this looks in a concrete example. We have here a small search space, nothing fancy, 2 dead ends, D1 and D2. And we have shown last year already that for certain heuristics we can find basically a set of no successor that contains this dead end. And this is then used as an argument that this state is dead. So this is basically very similar to what I showed before with the inductive certificates. Proof structure is very similar, so at the end we have that D1 is dead. Then the second part of the proof, we do the exact same thing for D2, and again, as we see, this has nothing to do with the proof that D1 is dead. And what is left to do is basically we just build a set of all the dead ends, and through this rule D2 we can basically iteratively argue that this entire set must also be dead, because we have shown that every single state in it is dead. And then the last step is simply saying, well, from the expanded states I only get to themselves and to dead states, and this is why the expanded states are also dead, and because I is in the set of expanded states, I is dead and the task is unsolvable. Now, we also implemented this, so we implemented both the generation of proofs and an independent verifier that can verify those proofs. And we ran experiments on those following algorithms, so a star search with Hmax, a star search with merchant shrink, and a star search with H2. And also to show how this combination of different heuristics works, we also ran a configuration A star search with the maximum of merchant shrink and H2. And we also implemented it on the clause learning state space search from Steinmetz and Hoffmann from 2016. So just short, the limits were for the generation of the proof, or generally running the planner, standard 30 minutes, 2 GB. For verifying the proof, we allowed the verifier a bit more time, 4 hours, but also only 2 GB of memories. Now here are the coverage results. This was run on a bit less than 700 unsolvable problems. The base column says how many tasks the planner could find out that it is unsolvable without actually creating a proof. Certifying is the same thing with the same limits, but it additionally also creates a proof. And the verifier is just for the proofs that we have, whether it could be verified within the given limits. And as we see, it's actually quite promising, the results, so we can generate proofs most of the time within the same limit that we gave the planner without generating proofs, and we can also, almost all proofs we can also verify within the given limits. And the numbers in brackets that you see here, these are the numbers for the inductive certificates, and we see that we compare quite favorably to those. The only part where we are doing a bit worse is the merchant shrink heuristic, where we could generate a bit less proofs, but we can still overall verify more proofs. And by the way, also all the proofs that we generated were verified to be correct. Although for the class learning state space search, we at first did not have that. So there were some certificate or some proofs that were deemed invalid. And when we looked into it, we noticed that the algorithm also uses certain additional mutex information, which we at first did not include in the proof. And once we did that, then the certificates were also valid. So to wrap up, we introduced a compositional proof system which allows now, in contrast to the old system, to combine different approaches of planning. It covers a wide area of planning techniques, and we can both efficiently generate and verify proofs with this new proof system. In future work, we would of course like to include more techniques such as partial order reduction or flow and potential heuristics. And we also believe that in order to achieve that, we will actually need to extend our proof system, include new rules, new basic statements, which should still be efficient, but would allow our proof system to become more powerful. Thank you very much for your attention.
Okay, we got time for some questions. Do you want the mic? We have to
My question has to do with... please rely.
Okay. I don't dare throw it anymore.
And then extend these ideas for optimal planning. In other words, can you prove that certain sets have a lower bound? And remember that information and then use that as to cut off parts of the search space.
We were thinking about that already. We didn't really pursue it yet. One simple way would be to just encode the actions into, or the cost of the actions into the actual actions, and basically that, like, you start with a budget of allowed costs, and then you just decrease it with each action, and once you reach cost zero, you cannot apply any actions. Then this approach should work exactly the same, so you can kind of prove a lower bound with this. But it would probably also blow up a little bit.
Can you command others? Huh? Okay, I'll ask my question on the way. That's a good idea. Can you comment on what those proofs look like? For example, for a heuristic search of H max, I mean, it seemed to me like you're going to basically say, list all the dead ends and then list all the states before them, so basically spit out the whole state space, or can it be more complex?
More or less we built, what we actually did is we built a BDD with all expanded states, and yeah, we listed all the dead ends explicitly in those proof steps, and then kind of built a set incrementally with all the dead ends. So it looks a little bit long, it's maybe a little bit how do you say, like, it repeats a lot, but this allows the proof structure to be really clear. And yeah, so that it really works with this very syntactical approach. But one other thing that is also good, even though it sounds like very long proofs, the size of the proofs were actually, where we could compare them, in general less smaller than the inductive certificates.
How far away do you think we are from using this sort of thing in the next unsolvability IPC? What are the major hurdles that will need to be overcome?
That's a very good question. I'm not entirely sure. So, I mean, we've shown for quite some techniques how this can be done, and I think it is quite powerful already. But of course, the question is, like, if you come up with a good new idea, how can you show unsolvability? It's probably also an additional hurdle to think about, well, how can I build this into the proof system? And I can imagine that there are certain techniques that at the moment we couldn't cover. So, like, for example, partial order reduction, I don't think that would work with just this proof system. But I hope that we're getting there at some point.
Okay, there would be time for one more quick question without a mic. Anybody? Okay, let's thank the speaker again.